computation.
I think it was something along those lines.
Yeah.
But yes, the computation module he taught me, there seems to be a lot of content
Oh, okay.
that I saw.
Cool. Thanks.
I'm not sure if I have any microphones, but
Did you want to check the?
we're
Not
going
now.
to kind of show portions of this.
Okay.
Hello guys, if I can have your attention now. Thank you all very much for coming to our first today we've got Dr. Felix
Hovsepian.
Hovsepian, and he will be talking about 10 things that you need to know about computation and AI. This will be a very introductory talk. This will also cover a lot of research development as well. Felix got 2 degrees in Warwick. His first one was in maths, and his second one, sorry?
My second one was in common sense reasoning in computer science.
Common sense in computer science, something that we showcased while trying to get the talk up and started, and a number of other books, publications, and advices on government boards as well with regards to the subject. Currently, he's doing consultation work with Turing manifolds, hence the logo of Turing. And without further ado, I thank you very much for coming to give us this talk, and thank you all for coming as well.
Thank you very much. Thanks. So I can see that some of the talks were planned to be on deep learning. I decided not to give one on deep learning deliberately because it's relatively easy to find up-to-date and readily available information online. It's, you know, if you Google deep learning tutorials, it's very difficult not to find one. So my passion, I started in Warwick in pure mathematics, went away, 10 years later came back and did a PhD and 2 postdocs in computer science, primarily based on reasoning, computer reasoning or machine reasoning as opposed to machine learning. And we're talking many years ago, so my master's, where I first encountered stuff that I'll cover in one of the talks, I looked at things like fuzzy logic, neural networks, and ended up doing a project with British Telecom on speech recognition. And then I came to Warwick because there was a chap here called Tony Cohen, who was one of the world leaders in theorem proving. And so I wanted to learn about sort of computational logic and how do you get machines to reason. So all in all, I was a student and a postdoc, etc., for about 10 years at Warwick. And L3 brings back a lot of very fond memories because I had my first year lectures in here, and that would have been 76. So Warwick has been very kind to me over the years. One of the things that I decided to talk about today was really 10 things that I thought you should know about computation and AI. Because whenever you get onto social media, you get on the internet, and people talk about AI as if machine learning is all there is. And there doesn't appear to be very much in the way of acknowledging just how wide and deep this subject is. And so I thought I would tell you some stories, because that's, after all, what we human beings do. We tell stories. So number one, who started all of this? You know, we like to point fingers like, okay, who's responsible? And it turns out that it was Leibniz. So all of the things that people like to talk about in, you know, the good old-fashioned AI didn't work, I'm going to show you that's absolute gibberish. And the fact that people normally say, oh, well, it started in 1955, well, have I got a surprise for you. 1672. 350 years ago was when all of this started. Now, Leibniz was trained as a lawyer and a philosopher. So he wasn't even trained as a mathematician, and he didn't start doing maths till he was 26 years old. And I decided to show you this equation because that was his favorite equation. In fact, he claimed this was the thing that he would like to be remembered for. If you look in Turing's paper, the original 1936 paper, you'll find this equation used by Turing to show you why pi is computable. In 1672, he designed and built a 4-function calculator, which was the first one the world had seen. Prior to him, there was Pascal, and they did some, I think it did addition and multiplication, but this one did division and subtraction as well. The mechanism he used was used for 200 years, and it was called the Leibniz Wheel. While building this thing, he sort of reverted back to his philosophical days and thought, well, if I can build a machine that does arithmetic calculations, maybe if I had a language that captured human thought, I could build a machine that essentially did the same kind of calculation for thought. And that's basically what happened about 16 years later in 1688. He wrote a short document talking about the ratiocinatorus, which is the machine that would calculate, it would reason symbolically. And so he thought to himself, well, if I have a machine, then I need a language to go with it. I need an abstract, a clean language. And that's what was the Characteristica Universalis. So in fact, Leibniz started to work on symbolic logic because he wanted to build this machine. So as you can see, the whole idea of AI was to build a language, a formal language, together with a machine that you could process, the machine would process and reason. Number 2 is Entscheidungsproblem. In fact, just before coming in, I mentioned that I used to hire people, and they would come in with a computer science master's degree, and I would ask them, what does this mean? And I was stunned at the number of people that had not even heard of it, never mind describe it. Entscheidungsproblem, people always imagined that it came from Hilbert and Ackermann in 1928. In actual fact, it goes back to Leibniz again, because he's thinking in terms of this machine and what will this machine do, and the idea of the Entscheidungsproblem is that it means, in German, it means decision problem. So the problem he envisaged was, okay, if I have this abstract language and I put a statement into the machine, then how do I know whether I'll get an answer back? And that's basically what the Entscheidungsproblem is. It says, if I put a statement in this formal language, then the result should be a yes or a no. So it's a decision problem. It was cleaned up by Hilbert and Ackermann in 28 and became famous at that point. But as you can see, there was quite a gap from sort of the late 1600s to 1928. And the way it came down was basically, does there exist an algorithm to decide whether a given statement is provable from the axioms? So it's about provability. It's not about truth, okay? And that's one of the things that I think is so important, because a lot of people imagine that Gödel's theorem is about truth. There are true statements that cannot be proved. Really? Read Gödel's papers recently? 4 people responded to this problem. You can see that Gödel was quite near the date that it was announced. So in 1931, he published a paper. It wasn't called incompleteness. It was called undecidable, formally undecidable propositions. I've shared the PDF for these talk, and you're more than welcome to get a copy from the organizers. I've mentioned the various papers. If you are interested, look them up. It's interesting that people talk about Gödel and Turing, obviously the Turing machine. Alonzo Church beat Turing by a few months, and he did the, all of these proved that you couldn't do it. So the Entscheidungsproblem, the answer is negative. There does not exist a method or a process that will produce this yes or no decision. Alonzo Church did the paper in '36, beating Turing by a few months, and that became the Lambda Calculus. And for anybody who's studying computer science, the Lambda Calculus is essentially your bread and butter when it comes to theoretical computer science, as is the recursive function theory, which came from Gödel. Turing machines came from Turing, and very few people remember to mention Emil Post. And Emil Post's solution is very close to Turing's, and in fact Turing has a tape, whereas Emil Post has a 2D memory. There are differences, but they are very close, and I don't really know why they don't mention it. So I'm a grumpy old man, you know, I've been here for a while, and so, you know, the fact that Gödel took a lot of care in writing this paper, and then we get nonsense like this on the internet. You know, maths has a flaw. There's a hole at the bottom of maths. And that's typically coming from people who've rarely studied the subject or have asked somebody else. There is no hole at the bottom of maths. There's nothing wrong with maths. And in fact, what Gödel did was basically show you can't boil maths down into logic, which was the sort of the flavor of the month at the beginning of the last century. So you cannot mechanize the whole of mathematics. That's what Gödel showed. There are pieces of mathematics that mathematicians do that involve something other than this mechanical proof. So there is no fatal flaw. You know, why this bothers me is 12.5 million people watch this video, and it's not even right. So just to give you an idea of what is a Turing machine, at the time that Turing was thinking about this machine, so his mentor, Max Newman, basically taught a course on logic, and he said, there's this wonderful list of problems from Hilbert, and he described the Entscheidungsproblem. Well, at the time, they didn't have machines. They just had humans who were doing calculation from mechanical calculators. And you can see here that, you know, they're basically using squared paper and they're doing some kind of arithmetic. So he modeled this. He said, right, so there's a book of instructions, you know, how do you multiply numbers? There's some squared paper, a pencil to write the numbers down or erase them. And then he said, well, that's awkward, that's 2D. But in reality, I can kind of cut this up and make it into strips, and it basically looks like toilet paper. So all I need is something to read, write, a book of instructions, and basically a tape, paper tape. Now, you have to remember Turing was a mathematician. He's not trying to invent computer science. He's trying to solve a mathematical problem. So what he's doing is essentially modeling the human computer. And there you have it. So how did the Turing machine work? Well, he had a head that went up and down the tape, one square at a time. So if you're on this square here, the only operation you can do is read it, write it, move right, one square, move left, one square. So those are the only operations you have. Now you remember he's trying to model a human computer. So the human computer has some kind of mind and it's in a state, right? I'm depressed, I'm happy, etc., etc. And so this instructions book that was mentioned, it says, okay, if the head is looking at this square, the word he uses is, instead of really saying observing, he says it becomes aware of the value in that square. So in this case, it's 0. It looks down this column here. 0 says, go right 2 and print 2 in the square you see. So it goes to the right twice, prints a 2, and it says when you're done, the next state is 2. So the state is being described as the page numbers. So this isn't sequentially going through the instructions book, because it's saying once you've moved to this square here, printed the number 2, then go to page 2. So depending on what you see, what the machine sees, what it observes in the box will determine which page it ends up on and what it needs to do. So that is an intuitive description of what a Turing machine is. And from this, he was able to show that the Entscheidungs problem could not be solved. And it also is the beginning of theoretical computer science, because that is what today we describe as the definition of an algorithm. So the difference between a calculation and a computation is that a computation consists of a chain of steps that follows a well-defined model. You have to have a model for a computation. The calculation is typically something mechanical, but there is no model to follow it. Now that seems mind-bendingly abstract. Why would we want to do this? Well, because we can abstract it even further. And if you have the rules, the model that says if you are here and that's what your state looks like, then the next state looks like this. So we're going essentially from numbers to patterns defined by a particular model. Models of computation. Like I said, I'm a grumpy old man, and it really bugs me when people sort of say, oh, we need to teach everybody to code. To code in what? Well, Python. Right. So Python is what? It's a sequential language, typically. It's, well, up until now, they're trying to redesign the guts of it, because in terms of concurrency, it's miserable. And if you talk to a lot of people who get taught, you know, who are self-taught, and you say, okay, tell me models of computation, invariably they either talk about object-oriented or they talk about sequential, imperative languages. But in fact, there are many more. There are functional languages like Haskell. People doing computer science probably see it in year 2 or 3. The functional began life with John McCarthy and Lisp. There are logical languages, which I'm not sure people teach anymore. Anybody do Prolog? Oh, cool. So yes, they do exist. And there are various concurrent models. So threading is just one model, and it's not even a decent model. One of the nicer ones is called the actor model by Carl Hewitt. And by the way, it came to life in 1973, so it's not a new idea. Concurrency is typically quite a difficult concept, and programmers don't like to deal with it if they can help it. But concurrency is not parallelism, okay? If you go on YouTube, have a look, Rob Pike, and he will tell you why concurrency is not parallelism. Number 5, Claude Shannon. Now, most of you have probably heard of Claude Shannon because of information theory. He's the man that makes pretty much all of the internet possible. If you remember, in the olden days, you used to have CDs. He made those possible, modems. So most of the time, we look at Claude Shannon as the father of information theory. It gets much more interesting. He did 2 degrees in 36. Notice the year, 36. All the other people did their solutions in 36. There's something odd with mathematicians. All of a sudden, you'll get a bunch of them coming up on a particular year. It's a bit like buses. You wait forever for the bus, and then there'll be 3 in a row. So in 1936, he does an engineering degree and a maths degree, goes to work for a chap called Vannevar Bush, which was an analog computer. A year later, he writes his MSc thesis, which is known to be one of the top MSc theses of all time, primarily because it solves the problem of Bell Labs. Bell Labs had a problem that they couldn't get phone conversations to go across America, and one of the things he does is basically cleans up their switching circuits. Vannevar Bush turns out to be his mentor, and he says to him, you need to go and do a PhD. Mentors do that. And now imagine that he's a mathematician, electrical engineer, he's working for Bell Labs, you know, telecoms, relays. What does Vannevar say? Go and do genetics. So Shannon's PhD in 1940 was a formulation of genetics. So it's mathematical genetics. 48, another one of his interesting years. So Shannon writes up his mathematical theory of communication. By the way, if you Google the bandwagon, you'll find that Shannon is complaining about the hype of people using information theory, much like we have a hype going on with AI today. And that was in 1956. He basically leaves the field of information theory. We're back to Turing, 1948. He's talking about the child machine. If you have a look at some of the papers that he writes in this period, sort of 46 to 48, you'll discover that he's talking about neural networks. But the neural networks that he's talking about is significantly different to the ones that you see around today. Notice how hierarchical and geometrically beautiful this thing is, and look at this particular thing. And that's because this is essentially built on algebra, whereas Turing was thinking in terms of topology and geometry. So in there you've got neural networks. He's also talking about genetic algorithms. He's talking about self-modifying programs. After he comes up with the universal machine, he says, so on this tape that I have the data, I could also put the code. So it doesn't need to be just data. I could put program on the tape as well. But then the program will change the program that's on the input. And so he comes up with this idea of that there is no difference between code and data. It's the same stuff. So you can have a machine that changes its own code while it's running. And if you program in Lisp, you can actually do that and watch your own code being modified while the thing is running. It's absolutely beautiful. And in fact, that, after I'd seen that, was the pivotal point in my career, because I was doing cosmology at the time, and I switched to computer science because I thought, this I got to see. And it gets even more interesting. Look at this. He says, well, this learning thing, it appears to be something that emerges when you have two forces, reward and punishment. Anybody work on reinforcement learning? Have you played it? Does this look familiar? 1948. And not only does he talk about this, he actually builds a mathematical model that shows it. And that appears in 52 in the paper called The Chemical Basis of Morphogenesis. Anybody seen this paper? Can you see why I'm trying to kind of broaden the horizon a bit? I'm trying to cover material that you won't see in your typical courses, whether it's computer science or maths or biology or anything else. You know, just on the side, while he's got nothing else to do, he also writes a computer chess program. So he gets together with his chum called David Champenow, and they write a chess playing program called Turbo-Chump. Now bear in mind, there is no hardware at this point. There are no, I mean, you know, there are machines, but there are no computers. So he's written a program for a machine that doesn't exist. And so what he does is he pretends to be the CPU, and each move takes him 20 minutes. Two of his other colleagues from the Bletchley Park era, they developed one called Machiavelli, and he basically plays one off against the other. This name, Sean Wiley, will appear again in my slide deck. Gary Kasparov, on his centenary, played the program that, I mean, they basically implemented it. So they took the program Alan Turing wrote and implemented it. And the damn thing worked on a modern machine. So that's the bar that you should be setting yourself up for, not the nonsense that you see, you know, around you, because that's the kind of software we should be building. This idea of fail fast, you know, build it and it doesn't work, and patch it and build it and patch it back, you know, that's great. Let's say you do it for something like a big project where human lives are at stake. You know, there is no fail fast. Margaret Hamilton wrote the code that sent 3 astronauts to the moon and back. And in the 50 years since then, I think they've found maybe 1 or 2 bugs in her code. And this is stuff that sends, you know, I think it was the Apollo series, so she wrote the code for the first Apollo mission, which took 3 men to the moon. Anyway, so Gary Kasparov basically is just in awe of this program. And by the way, it's still a pretty good program. I mean, it will wipe the floor with your average chess player. This isn't sort of just a proof of concept that they did. Point number 7. 1948. Crikey, everybody's in there. Whenever you see something about what is life and the physicists get going, you know, they get excited, and, you know, Schrödinger talked about life and what have you, it turns out Schrödinger got it wrong. And that was pointed out by the Nobel laureate called Sidney Brenner. And in fact, it was so wrong that he called it Schrödinger's fundamental error. And it turns out that von Neumann wrote a paper called Self-Replicating Machines, which he presented at a conference in 1948. It's a famous conference. It's called the Higson Symposium. And in that, he describes how a self-replicating machine works. It turns out to be the right mechanism for DNA replication. That was 10 years before Watson and Crick. Any biologists in the room? No. 10 years. So von Neumann had figured out how DNA replicates 10 years before the people who did in physics and biology. And the reason Schrödinger gets it wrong is because he doesn't do what's said here. And I'm not going to read it, because you can read it faster than I can. By the way, if you have a look at some of the presentations by Nobel laureates in biology, you'll find that they're still talking about Schrödinger's book. Very rarely you'll see them talking about von Neumann's papers. By the way, this von Neumann paper that mentions how self-replicating machine works is what motivated John McCarthy to get into AI. So the paper that everybody mentions by Turing is the 1950 paper that appears in Mind. A couple of things that I think is important is you can see here Turing is saying, if you get this thing to be intelligent, then it's going to have programs we're not going to be able to make any sense out of. And not only that, he also in there says that it will make errors. That's just the nature of the beast. If you want intelligence, you've got to accept that at times it's going to go wrong. Cannot make sense. Isn't that amazing that if you have a look at some of the papers that are being published in explainable AI and AI ethics and how we should build this stuff into the design of these programs and how the programs must be flawless and they must explain themselves, etc., Turing said, ain't going to happen. But yet we still have this problem of people sort of saying, how are we going to build machines that will not make errors, etc., etc. 1943, Turing spends a couple of months with Shannon. And interestingly enough, Shannon switches out of information theory and gets interested in machine learning. In 1952, he builds Theseus, which is a mouse. Now bear in mind, we're still not, 1950 is about the time that a real computer begins to appear. So he's at Bell Labs. What has he got? Telephone relays. So this poor man built a mouse that effectively solves the maze using telephone relays. Well, he's an electrical engineer. I mean, what did you expect? Give him anything at all, he'll build something. But 52, Shannon is already into machine learning. 55, 3 people write a program called the Logic Theorist. And the Logic Theorist solves 38 of the 52 theorems in Principia Mathematica by Russell and Whitehead. And this program was before the famous Dartmouth conference. So when you get papers by Google saying, we've achieved this fantastic, thing, we've managed to prove theorems, etc. Well, hello, 55. We know how to prove theorems. I mean, I was building theorem provers here at the University of Warwick in computer science in 1985. We know how to do theorem provers. That's not, that's not rocket science. 55, there's a really interesting, all of this stuff is online for free if you were interested, is the proposal for the Dartmouth conference, which is the first appearance of the phrase artificial intelligence. Now, how they describe it is an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. That's what AI is about. Notice it's quite broad. We'll form abstractions. Have we done that? No. We'll form concepts. Have we done that? No. So in reality, and will improve themselves. Well, we've done some of that. That's what learning is all about. But in reality, there's so much in that one sentence that we've not really tackled yet. Pictures of the people at the Dartmouth conference. Notice Claude Shannon. Everybody talks about John McCarthy and Marvin Minsky. I have a feeling, and this is part of the book that I'm currently writing, that the real man behind all of this was Claude Shannon. Because he was the senior member of the people here. He's the one that worked with Nathaniel Rochester from IBM, who initially put up the money, and convinced, John McCarthy and Marvin Minsky were actually working for Shannon during their summer months while doing PhDs in Princeton. So they knew one another, and they also got to know Claude Shannon. Arthur Samuels does the definition of a machine learning. Not many people talk about Ray Solomonoff. Anybody ever heard of Ray Solomonoff? Oh. Yes. he's the first person that talks about probabilistic machine inference. So number 8, remember Ray Solomonoff. He's also the guy that does the algorithmic information theory and talks about Kolmogorov complexity. Now, he discovered Kolmogorov complexity independently from Andrei Kolmogorov. But Kolmogorov was interested in randomness, whereas Solomonoff was interested in inductive inference. So what Ray Solomonoff does is he basically writes reports called an inductive inference machine during the Dartmouth conference, and he's handing it out to people and saying, by the way, this is how machine learning should be done. It should be, the important thing are these things called training sequences. And it should have so the probabilistic machine learning starts in 55. That's very convenient for people not to kind of remember that. Because they can say, oh, look, you know, none of this stuff worked. We look at what we've done in the 21st century in the last 10 years. Look at the advancements we've made. But really, the ideas were laid down much earlier. Arthur Samuel defines machine learning, the term machine learning, as the field of study that gives computers the ability to learn without being explicitly programmed. Now, Arthur Samuel writes a program. I mean, these people are, you know, they're not just theoreticians, you know, they pull up their sleeves and they start writing code. You have to imagine the machines that they had available to them. I mean, we're not talking 4-bit microprocessors. You know, that's not even within their dreams. But anyway, so he writes a checkers playing program that beats the checkers playing, the 4th ranked checkers playing person in the US. So I would say that passed, that worked. What's more, the kind of ideas that he had while he was building that program becomes the first non-numerical computation, and the ideas were then used by people who were designing operating systems for IBM. Number 9, definition of AI. You cannot believe how irritated I get when people say, oh, well, AI doesn't have a definition. Yes, it does. The fact that you don't like it doesn't mean it didn't have a definition. If you go onto YouTube, you will find, this is in fact a sort of a screen capture from the televised version of the Lighthill debate in 1973. You've got Donald Mickey, John McCarthy, and Richard Gregory. This is a terrible screen capture, and the video is not that brilliant either. There's a guy there, and he's called Mickey Larkham. And I'll tell you about Mickey Larkham a little later. So the definition McCarthy has for AI is that it's a science. It is the study of problem-solving and goal-achieving processes in complex situations. That's the definition of AI that McCarthy gave. Now, he did give one more later on, but it's pretty much in the same spirit. And off the bat, he rules out, he says, I don't care how humans and animal brains work. That's not what this is about. So this isn't cognitive science, okay? This isn't psychology, this is AI. This is about problem solving. How do we get machines to solve problems under these circumstances? And for, you know, you're welcome to sort of follow me or connect with me on LinkedIn, and I'm forever having discussions and dialogue with people who are psychologists and say, you know, you don't talk to us because we know how brains work. What do I care? McCarthy specifically says, distinct from. He's not talking about human brains. He's saying, you know, what would it be for a machine? That makes the problem a lot harder. If you want to talk about common sense, you have to pretend you're a machine. Well, what does common sense mean? And that drags in a lot of philosophy. It becomes very difficult. There is another definition, so part 9 is kind of A and B. There's a chap called Eric Horowitz, who's the chief scientist at Microsoft. And he really is a doctor. I mean, not a PhD, I mean MD PhD. So he worked in Stanford, he did his medical doctorate, and then he got his PhD. And he says, oops, AI is the scientific study of the computational principles behind thought and intelligent behavior. People don't like this and argue that this is sort of circular. But if you just give it a chance, this is a pretty good definition. And one of the reasons I like it is because he talks about the 4 pillars of AI. So he's read the proposal and he's distilled it. He says, basically, if you want an AI system, the system has to have the capacity to perceive things, to learn things, to reason, and to be able to communicate using natural language. So let's talk about things that have happened to Warwick, the staff and researchers at Warwick. You remember Sean Wiley, the chess playing guy that wrote? So I talked about how Turing wrote a program with Champenoux called the two-row champ. And Machiavelli was Donald Mickey and Sean Wiley. There's Sean Wiley. He was at Bletchley Park and worked with Alan Turing. But the connection to Warwick is that he was Sir Christopher Siemens' PhD supervisor. And you probably don't know Sir Christopher Siemens because he passed away probably while he was still at school. But you have a building named after him. So that's what Sir Christopher Siemens looked like. And he was an amazing teacher. I mean, I had him for a course, and he also mentored me when I started my PhD. So he was an incredible mathematician and an unbelievable teacher. And we believe he got that by being mentored by Sean Wiley, because Sean Wiley was an incredible teacher and an incredible human being. I mean, he was a distinguished mathematician, and after he retired, he became a math teacher at a local school. So he really loved teaching. The Ratio Club was basically where a bunch of people met, and they talked about cybernetics. It started in 1949 and lasted till 55. There's Turing, so he was in the Ratio Club, and there's a chap called Donald McKay. Donald McKay was a significant member of this kind of cybernetics club and talked about information. What is information? And he's got a little book that not many people read. I think it's absolutely brilliant. Anybody know who this gentleman is? Any maths people here? Have you met Robert Mackay? Notice the last name, Donald Mackay, Robert Mackay. Donald Mackay was his father. So the maths department has a connection to some of this stuff. And Robert Mackay now does complexity science. So he used to be the person leading that group in the maths department, but I think it's now switched to somebody else. For those of you in computer science, and I have been trying my very best to get the university to do something to remember David Park. When I arrived, I was a teaching assistant for David Park in a course called Foundations for Computer Science. And at that point, you know, I got to know David Park quite well. He was an incredible human being, and he literally, I mean, it's difficult to describe just how far his thinking was ahead of the rest of the, not just the rest of the department, but pretty much everybody that I could think of. I just felt that when we went into a staff meeting, the rest of us were kind of wearing loincloths and carrying around sticks while he was arriving in a spacesuit. I mean, this guy was years ahead. He was at MIT in the late 50s and knew the people that were building AI. In fact, he was an assistant for McCarthy, and he was instrumental in not just the theory of Lisp, but also its implementation. So David Park was a computer scientist, a theoretical computer scientist, and was one of the meanest programmers I have ever met in my life. I mean, this guy could code people under the table. He was an amazing, I mean, he would design languages from a theoretical perspective. He would do the domain semantics for the thing, and then he would implement it. I mean, he would, you know, whether it was an interpreter, a compiler, or what have you, all of a sudden you would have the whole language and the whole stack of the thing. And in fact, if you go and have a look in the Lisp 1.5 Programmer's Manual, his name is in there. This is a chap that he worked with and knew, you know, they were colleagues at Stanford. David, and I've put a little image down here just to remind me, David Luckham has written a book called The Power of Events. So for those of you who are interested in event-driven or reactive programming, you need to read this book. It's about complex event processing, and it's years ahead of what you will find in reactive libraries. Some of you may have seen Professor Mike Patterson around. He's definitely, you know, still around and very much active. Mike Patterson was David Park's PhD student. So that's the connection there. Mike Patterson was Les Valiant's PhD supervisor. So in terms of computer science, Warwick has among some of the top computer scientists, or had some of the top computer scientists in the world. Les Valiant is currently in Harvard. He won the Alan Turing Award. And all three are FRSs, so they are very impressive people. If you have a look at some of the work that Mike Patterson has done, it's pretty impressive. I mean, he's publishing, you know, he retired a while ago and he's still publishing, and the papers are still winning awards. So this idea of maths being a young man's game is just not true. The reason I showed this is because in, I think this was around 2012, maybe. Les Valiant is talking about some of the research he's done on machine learning. And he says, and he's talking about Turing, and Turing basically says, yeah, you've got to put sensors into the machine. The machine also has to be autonomous, so it's got to walk around, it's got to be able to observe for itself. And he says, you have to study AI for 40 years to understand that one, because that's hard. So to get a machine that has the ability to observe and to behave intelligently, to communicate in natural languages, to have the sort of the neuro capabilities for autonomous behavior is very difficult. So just to sort of wind things up, I just want to give you a quick tour of where I was. My mentor was and still is Ian Stewart. So I don't know if anybody's come across Ian Stewart. Have you actually met him? He's a great guy, isn't he? So may God bless him. I mean, he's been my mentor for about 40 years. And it's a wonderful experience when you can sort of go and have coffee with somebody who's basically seen your entire adult life, you know. And I get to hear stories from his side that I didn't know about. So it's great. He's written a book with another person who was my undergraduate supervisor called David Tall. So those of you who've done mathematics, you've probably come across the Stewart and Tall book on foundations of maths. Ian Stewart was instrumental in me learning about nonlinear systems, and I really am grateful because they are so different to linear systems. And at the time, I took a course from him And here's the book that came out of the course. I don't think that book was out when I was doing the course, which he wrote with a chap called Tim Poston. Not Tim Poston. Tim Poston and Ian Stewart were basically friends while they were doing PhDs. Sadly, Tim Poston has passed away, but he did amazing. He was a true geometer. After getting my bachelor's from Warwick, I went off to Deloitte, spent a couple of years becoming a management consultant, only to realize that there's something about maths. It's in your DNA. You can't let go, you know, it's not. So there are some people that do maths because they just want a degree, they get on with their lives and they live happily ever after. Then there's the rest of us, which are inflicted by this desire to go back and have these abstract thoughts. So while I was in Cambridge, I went into, I think it was Heffer's, bought myself this book, and chapter 6 was on causality. And I got very interested in causality. I wanted to understand causality, so I took the book and went and saw a chap in King's called Professor Bonner. And I said, I would like somebody like you to help me understand chapter 6, please. And so he kindly took me on as his student, recommended that I should go and attend classes by Felix Pirani on differential geometry and differential topology. Felix was another incredible teacher. I had horrible teachers in my school apart from Colin Lomas. It just disaster. And then I came to Warwick. And I was fortunate that I had some of the best teachers at Warwick, and then when I returned to King's, I had, you know, the likes of Felix Pirani. By the way, Felix Pirani also was instrumental in helping Roger Penrose get into relativity. Felix Pirani was a double PhD, his first one being from USA in quantum gravity. While I was doing all of this, I was introduced to computation by Malcolm McCullum. Malcolm McCullum had George Ellis as his PhD supervisor, so there's a connection there. But Malcolm, I was doing some tensor calculations. Tensor calculations are symbolic, and he said, you know, you're spending hours doing these calculations, why don't you use the software? Now, bear in mind, I was taught programming at school. So this concept of, you know, I was taught programming when I was 13 years old, well, so was I. The only difference being that I was using punch cards that had to be sent by mail to the university to be processed and then sent back. So syntax errors were a total nightmare. You had to get the damn thing right. That was 1971. I was taught Algol here as an undergraduate, so I hated what I was taught in 71, I hated Algol in 1976, you know, didn't like programming. All of a sudden, Malcolm McCullum introduces me to a program called Sheep. It's a package written in Lisp. And this thing does symbolic computation. I'd never seen anything like it. No numbers. It's not about approximate equations, it's about doing the thing in symbolic form. So in terms of it's doing tensor calculations symbolically. This is 1981, 82. That was the pivotal moment. I fell in love with Lisp. And I wanted to know, how is this thing working? And it was to do with theorem proving, to do with proof assistance. And that was really the beginning when I decided that, you know, as much as I love doing causality, and my supervisor had introduced me to the work of Kurt Gödel, and he said, what you need to do for your thesis is do some of the research on causality from Gödel. Trust me, that has to be the single most difficult stuff I've ever encountered is the work by Gödel. It took me like 10 years to understand the damn thing. So at that point, I switched out of being a cosmologist and into computer science. By the way, Oscar Morgenstern, who was a friend of both Einstein and Gödel, basically says Einstein, towards the end of his life, had just given up. He said, I only come to the institute so that I have the honor of walking home with girdle. I mean, that shows the caliber of this man. So I didn't want to go to computer science. It was like, I don't like programming. I don't like this idea of write a program to do the 8 queens. What for? I've been a chief technology officer for a decade. I've never used the 8 queens problem. So they have these things that they imagine are really useful. You know, you need to do this, and you need to do alpha pruning and what have you. Okay. So I thought to myself, well, I want to learn Lisp, and I want to learn this sort of processing, but I don't want to be in a computer science, so I went to engineering. So I became a systems engineer, and I was fortunate because at the time there were some really great teachers. If you want to learn about complex adaptive systems, this is a fantastic book. It's by John Holland. So the books that I read during that course was Cybernetics by Norbert Wiener, The Adaptation, Natural and Artificial Systems by Holland, and a book called Design for a Brain by Ross Ashby. When I came to Warwick, so I returned back in '85, I convinced Tony Cohen to take me on to do computational logic. Pat Hayes, so those of you who are in AI, Pat Hayes has written lots of papers on AI with John McCarthy. Pat Hayes was Tony's PhD supervisor, and he's the one that said, so I talked to him, and it turned out that Pat Hayes knew Tim Poston. So he said, because Pat Hayes had been a student of Christopher Siemens when they were in Cambridge. And he said, have you seen Christopher Siemens' work that he did with Tim Poston? And I said, no. And he said, then you might want to start thinking about common sense knowledge and reasoning. So that's the beginning of my PhD, which I submitted in '92. And people completely ignored it, and it was miserable. But all of a sudden, I just looked at it last night. I thought, well, hello. People have started getting interested in this thing. You know, so I have people who say to me, '92, you know, like last century, like forget it. All of a sudden, you know, common sense reasoning has become interesting. Why? Because DARPA put $2 billion into the pot for people to study common sense reasoning. Well, that's a nice motivation. If you want some money, this is what you got to do. And the reason they did that is because there are some challenges, read difficulties, with second wave AI systems, which are essentially the deep learning systems. The deep learning systems have this problem, which comes out of adversarial networks, that you can add a little bit of noise, and the system says, it's a panda. Wait a minute. No, I changed my mind. It's a gibbon. What's worse is the confidence with which it says is a gibbon, 99.3%, is more than the confidence it had that it was a panda. But you can see as a human being, the pictures look the same. So what DARPA did was say, okay, let's go to the third wave of AI, and we need the abstraction, the perception, the learning, as well as the reasoning, hence the 4 pillars that I mentioned. If you are a deep learning person, I would highly recommend you go and have a look at Ian Goodfellow's work. 2014, I think his PhD was. He has these dueling deep learning networks. And the one you want to look at is not the one that does it with statistics, but the one that uses game theory. It's very interesting. I think it's very powerful. And it's the one thing that scares the living daylights out of me when it comes to AI. What do I do in terms of interest these days is nature-inspired computation. In particular, I'm interested in collective intelligence. You can see the swarm intelligence, you know what they are. They're bees, they're flocks of birds, etc. They're distributed, decentralized, self-organizing systems. and they are amazing because they're composed of lots of individuals, but you're not focused on the individuals, you're focused on the collective. This thing here was built by termites. Termites can't communicate with one another because they don't have any senses. So they communicate via the environment. This structure keeps the temperature internally constant, and it also cleans out the dirty air, brings in fresh air, and is about 30 feet high. This isn't a little structure. Termites you can barely see with, they're millimeter things. So as a collective, they do amazing things, and I'm interested in how does that happen? How do you get a bunch of individuals that can communicate using messaging? They're amazing in terms of they're scalable, they're parallel, and they're fault tolerant. You can take a collective and literally wipe out half that collective, and it will function as if nothing has happened. I don't know of any other system that can do that. If you go and have a look, there are some really nice simulations by Craig Reynolds where he's talking about Boids, really easy to program. You can do it in JavaScript. 2 years ago, I supervised a research project on quorum sensing. This is bacteria that they sort of fluoresce. There are also these things called kilobots. Wow. Oops. That's okay. That was pretty close to the end. To stop, yeah. Absolutely. Sorry, I've overran. Yeah. Sure. Right. Absolutely. Yes. I think that the fact that we can take data and look for patterns is incredible. In particular, I used to build medical devices like X-ray systems. What's happened is the hardware technology has improved. So we can take pictures that are very high resolution, and the human eye can't see at that resolution. We need machine software to be able to help us to see some of the patterns. So some of the advancements are really not just in software, but because the hardware has improved as well. So being able to do those kinds of things is really useful. Today. Oh, sorry. Thank you. The dirty what? Sure. Dirty duck. Do you want to? Sorry about that.
No, it's fine. It's because we started really late because of all the technical issues we were having. We started about like
That's okay.
anyway.